Let's talk more about the properties of electrons. So far we've talked about one electron systems, a hydrogen atom with only one electron. We need to add more electrons to get to the rest of the elements on the periodic table. So we need to talk about groups of electrons. And electrons have special properties. So let's look at some of them. Electrons have a property called spin. Now it's called spin for kind of historical reasons because it behaves like a spinning charge. Electrons are charged, and if they spun around their axis, they would create a tiny magnetic field. Now, electrons undoubtedly don't spin about the axis. They might not even have an axis. No one's ever seen an electron. It's one of the interesting parts of science. No one has ever seen one of those things. We don't know what it looks like. But the electron has a property that behaves like it's spinning around an axis. Remember when we had photons and they behaved like they had momentum? The photons don't have mass, so they can't really have an mv momentum, but they have a property that behaves just like momentum, that photon energy. Same thing with electrons. They probably don't spin about an axis, but they have a property that behaves just like an electric charge spinning about its axis. So if an electric charge spins about its axis, it acts like a little magnet. So here I have a little magnet. Let's look at that. If you have a little magnet and you put it in a magnetic field, the direction that the magnet can point is influenced by that magnetic field. So here's a little bar magnet. If it's in a magnetic field or not in a magnetic field, depending on when I bring this magnet in, that'll determine the properties of this little bar magnet. Let's take the magnet away right now. It's in no magnetic field, so it can point in any direction in space. If I bring a magnetic field in and say, okay, now I'm going to put you in a magnetic field, now there's a preferred direction for this magnetic stir bar to point. Just like an electron, it has a preferred direction in a magnetic field. Here's a low energy direction aligned with the magnetic field. If I push it away from that low energy direction, I have to put energy in. And if I release my finger, it'll go back to the low energy direction. This little bar magnet can point in any direction with respect to the field. I can give it any amount of energy and have it spin back to its preferred direction in the magnetic field. For electrons, that direction in the magnetic field is quantized. It can only be spin up with the magnetic field or spin down against the magnetic field. Quantized energy levels, 2 of them. And we're used to quantization now for tiny particles. So we understand the electron magnetic field can't point in any direction. It can point spin up or spin down. Let's look at an experiment that manifests that. If you take electrons and you send them through an inhomogeneous magnetic field, they will separate based on their spin. Out here, where there's no magnetic field, they could either be spin up or spin down. As they pass through the magnetic field, that will sort them based on whether they're spin up or spin down. Now, if they could point anywhere with the magnetic field, you'd expect them to go through the magnetic field and just end up any old place. The ones that were pointing slightly up would go high. The ones that were pointing slightly down would go low. The ones that were pointing in the middle would go straight. But we know that the electron spin is quantized. It can only be spin up or spin down. So when you do this experiment, you get a group of electrons. The ones that were spin up end up and give you a bright spot here. The ones that were spin down give you a bright spot here. 2 possible orientations of the magnetic field for electrons. So we're going to call this property of the electrons their spin. We're going to give it a quantum number, m sub s, and we're going to let it have 2 values. Spin up, m sub s 1/2, and spin down, m sub s minus 1/2. Plus 1/2 and minus 1/2 will be the spin values for the electron spin. So that's another quantum number. So we have n, l, m sub l that defined the orbital, and now we have m sub s, which defines the spin of the electron. So 4 possible quantum numbers now can describe an electron about an atom. N, L, m sub l, and m sub s. Now it's interesting, this quantum number has a half integer value. All the other quantum numbers had this integer value of 0, 1, 2, -1, minus 2, etc. Now we have a half integer value. And you may wonder why that is. Well, it has to do with the strange properties of electrons. Electrons are crazy little particles. Like I said, no one has ever seen one, so we don't know what they look like, but they have strange properties that don't behave like normal particles. For instance, electrons have a property where if they were to go around a closed loop, they wouldn't come back to the same state that they were the first time. And that's kind of odd, right? You usually expect something. If you say, I'll take this and I'll go around in a closed loop, it should look the way it looked when it started. Electrons don't behave that way. They have a twist in their space relative to our space. And they act kind of like this device here. This is a Mobius strip. This has a twist in its space relative to our space. And if you send an electron in our space around a closed loop, and I'm going to send this electron around the Mobius strip around a closed loop, when I get back to where I started, I'm not in the same state that I started in. I have to go around this loop twice to get back to the same state that I started in. That's how electrons behave in our space, because their space is twisted relative to ours. They're very, very crazy little particles. We're going to look at now taking those electrons and placing them into orbitals more than one at a time. So we're going to move beyond the hydrogen atom to the rest of the elements of the periodic table and look at multi-electron atoms.